Right, this is the DC servo control system design experiment, and we have a number of aims to achieve here. The first one is to identify the transfer function of this DC servo down here. Then, having identified it, we can then have a go at using our feedback control theory to design a proportional control system on the DC servo and investigate the damping ratio and peak overshoot. Having looked at proportional control, we can then move on to proportional plus derivative control, and we can use this to have a higher degree of control over the DC servo than just proportional control. We can then use Simulink simulations to select all the different controller designs that we want, and then having done our Simulink simulations, we can then use those gains on the real servo to compare how the real servo behaves in our simulations. Now, if the simulations and the real responses are very close, we can conclude that when we came to identify a transfer function here, we did a good job. If they're not so close, either means we didn't do such a good job here, or for some reason the system was behaving in a non-linear manner. Now let's have a look at the learning objectives. So the ideas are to become familiar with second order system theory, which we've covered in semester 1, and know how to identify the parameters of a second order transfer function, and to calculate the damping ratio and calculate the natural frequency. We then want to look at how to calculate some proportional gains used in feedback control to set the damping ratio of the closed loop system. We then move on to use the proportional plus derivative controllers to set both the damping ratio and natural frequency of the control system, which gives us more or less complete control over the second order system with a PD controller. We're then going to simulate the second order system for the different controllers, that's the proportional and the proportional plus derivative, and then we can compare those with the real simulations and look at the effect of noise and maybe system modeling error on the overall performance. Now, if we look at applications of DC servos are widely used in industry for controlling the position of things. So one example might be you want to control the position of your steering wheel in an automated car. So there'll be a servo mechanism inside there, usually electrically operated, which will control the steering wheel to a given position, hopefully to drive the car on a given route. Other areas where they can be used are, as in, let's say you want to control the position of an aileron or an elevator or some part of your flight control systems, then many of the control surfaces on the aircraft use hydraulic or electrical servo devices to accurately control the position of these control surfaces. So there's practical applications of servo drives, and increasingly as automation comes along, servo drives are used more and more. The actual rig that we've got is here. It's made by Feedback Instruments, and it's a little DC servo. The actual motor is here. It's behind this shaft here. We've got this motor here, and it's a plus or minus 15 volts DC motor. So it's a fairly powerful motor because you can put over 30 volts across it as well, so it's fairly powerful. That then drives a shaft here, which drives a belt here. So this goes round a little bit slower. This goes around quite fast, it's a bit slower. And there's another belt here, drives around that way, so this one goes up even slower. So it's like two belts here. And so you've got three shafts, and this shaft then goes round, and it's the output of this shaft that we control the position of with a potentiometer attached to this shaft here. In addition, onto this main shaft, the main drive shaft, we've got a tachometer which can measure the speed of this shaft as well. So the speed of the shaft is quite handy because it's like a derivative of the position. So if we want to implement, say, derivative control, we could use the tachometer to give us the derivative signal. The control system, we're using a personal computer to do the control. So this is a PC here. We've got like a digital to analog converter, which converts a digital signal to analog, which sends an output to the servo motor. That's a plus or minus 15 volt signal going to the servo motor. The servo motor then drives to a certain position, and then we can measure using some sensors. We can measure the position of the motor and also the velocity of the motor, and those signals come down this way through an analog to digital converter and back into the computer. Now, the advantage of using the PC is that we can change the controller gains via the keyboard, and the inputs and outputs can be displayed on a monitor. So if we have a look at the typical responses, if we press O on the keyboard, it goes into open loop and we get an open loop response. This is time this way, and this is the position of the servo motor, the potentiometer, the output of the system here. We can press C, go into closed loop, and it'll give us a closed loop response. It inputs a set point as a red signal, and then we watch how the system responds in the green to the set point change, and we look for things like overshoot and time for peak overshoot in this response here. And if we press K, we can, this screen pops up, and then we can change the different gains in the controller. And we've got 4 gains to change: the proportional gain, the integral gain, the derivative gain, and the tachometer gain. So Kp, Ki, Kt, and Kv. In this experiment though, we won't have any integral, so missed that an A there. I won't allow you to edit it as you go along, unfortunately, but no, it's just been integral gain there. And so this is the test rig, and next thing we're going to do is move on to work out how to use the impulse response to obtain a transfer function of our DC servo. So this can be a handy method when you're designing control systems. If you've got a transfer function, you can then go into simulation, and you can use a simulation to work out good ballpark numbers for your controller gains. Otherwise, you're going to have to guess them, and guessing can be a bit dodgy. Okay, so here you've got a little video of the DC servo. Let's just have a look at what's going on here. We've got this is the DC servo itself here, and there's a motor behind here which drives this motor through a belt system here and another belt system there. So this is the output here. So we're measuring the position of this as an angle, and we're controlling it with a motor behind here. So I'll just try and show you the motor and the different parts by just rotating this over like this. Stand up like that. So if we have a look again, this is the motor here, and this is the potentiometer that's measuring the output here. So there's the motor, DC motor, there's a potentiometer that's measuring the output, and it's running through some gearboxes here. And the speed of the motor is measured using that tachometer there. Look at the screen. The red line is the output, is the input, sorry, and the green line is the actual potentiometer. So this is the desired value for the potentiometer. This is the actual value of the potentiometer, and the signal down here is what voltage we're applying to the motor. Now this can be limited because it can only go plus and minus 15 volts on this particular motor. So if it hits the 15 volts, it means it goes along that line there, which means the motor's like saturated. Now we can get different transient responses from the system. If I press K on my keyboard, I can now go into the part that changes the controller gains. So if I drop my gain down to 2 and 0, 0, 0, it'll now give me the same system but now with a lower gain. So at a gain of 2, we can see we've now got much less overshoot here. Just disappeared as I touched it. If we went for a gain of 1, it can be quite slow. Well, that's a bit slower. And obviously if we go for a higher gain, let's say 5, we start getting a bit of overshoot. So what we're going to try and do in the experiment is work out a transfer function for this whole system here. Use that then within Simulink to choose the right controller gains so as we control the shape of this transient response. And one of the main things that we're interested in is this overshoot here and the time at which that overshoot occurs. So that's the overshoot and time for peak overshoot. So this is our DC servo rig, which we're going to be using in the experiment. Just another point, I suppose. Looking down here on the keyboard, we can change KP, which is proportional gain, KI integral gain, which we're not actually using, then KD is the derivative gain, using the derivative of the error, and KV is using the tachometer gain from here. So we can either use the derivative of the error from the actual error, or we can use the tachometer signal. So we've got like two controls. We can have three controls: KP, KP and KD, and KP and KV. So we can look at three different controllers to see how they work. And then if we put some numbers in there, let's say 40.10, even, we can then implement our PID gain. So that's an example now of a PD controller running, and you can notice now that the signal on the output here is a little bit more bouncy because there's a little bit of noise in the rig, which you can see is like it's got a bit jittery. So this is our rig that we can experiment on. Last thing I'm supposed to mention is if we want to do the work out the transfer function, if we press O, we can go into open loop, and this does an open loop step response for us. So with the open loop step response, we can use this shape to identify the transfer function. Then, having identified the transfer function, we can use that then and our second systems theory to design the various controllers. I've just noticed this little lever's been pushed down here when I moved it, so it should be at the top. Now it's halfway down, which is messing up our experiment slightly. So when we do the experiment, make sure that this is locked in the top there. Otherwise you'll get some wrong results. So if you just go back now to the proportional control by pressing K, it goes back to, C, goes back to closed loop control, and if we now press K and put in, say, 10.000, that's quite a high proportional gain, we'll get sort of a fair bit of overshoot now in the control system, too much overshoot. So we want to try and avoid that overshoot in the design of our controllers. Right, let's look at how to figure out now the transfer function of a DC servo. So if you imagine you've got a motor here, got some voltage, DC voltage, which we apply across the motor, and it's got running against a load here, and so we'll have some output position theta of the shaft, and we're controlling the output position theta. So theta is our output, the input is the voltage. So if we think of a motor here and a rotor, it's got some moment of inertia J, and it's running against a load, and it's got some shaft position theta. Theta double dot is the angular velocity, and theta dot is the angular velocity. Theta double dot is the angular acceleration. So we can now apply the F equals ma to rotational system. So it's T, the torque on the motor, is equal to J theta double dot plus B theta dot. B theta dot is the load effect, and this is the moment of inertia of the main system with moment of inertia J. So we can get this simple equation here that Tm is J theta double dot plus B theta dot, and we can then just rearrange these, and then we can make use of our Laplace transforms, that theta double dot can be replaced by S squared theta, and theta double dot by s theta. So then that gives us this expression here, and we can rearrange this then in terms of the transfer function by taking this term underneath this one. So it's going to be k over s js plus b. So this is a typical transfer function now for a DC servo, and this is not in ideal format here. So if we can make that b into a 1, then it becomes into like our first order system form. So we can divide everything through by b. So k1 will become k1 over b. The s can remain as it is. This will become j over b, and this will become 1. And that'll give us a new set of parameters, which will look like this. And then this now looks very similar to our first order system model, where k would be the DC gain and t would be the time constant. Remember, k is k1 over b, and time constant is j over b. So this is our transfer function now for the system in a format that we can understand and manipulate, because it's in a first order transfer function form, k over ts plus 1, but this time it's got an extra s term in here because it's a second order system as opposed to a first order system. And the second order system is coming in from the fact that we've got an angular acceleration here. So now, because we've already got an s term in here, if we do the Laplace transform of this system directly for an impulse, the impulse Laplace transform is just 1, so therefore the Laplace transform of this would just be k over s ts plus 1, which is very similar to the step response of a first order system without the s in. So we get that the Laplace transform from an impulse looks like the same as the step response for a first order system. So it looks like k into 1 minus eta minus t over t, where the big T is the time constant and little t is time. But what we're putting in this time is an impulse. An impulse goes along, goes up, goes along, and then comes back down again. So step just goes up, whereas an impulse goes along, comes up, and goes down. So this is the impulse response to a system now. And by putting an impulse response, we can measure this distance as k. And if we take 63% of the total output and measure from here to here, we can get the t. So this gives us a trick now for identifying k and t in the DC servo transfer function, in the sense that we can measure that distance as k, draw a line along here at 63% of k, see where it cuts here, measure from the start to this point here. That will give us t, this will give us k. So then we can identify the k and the t in our system. But remember that we've done this for an impulse response this time, not a step response, because the transfer function's got this extra s term in there. So then we can move on to identify now k and t from the impulse response. Right, so here we have the system, the DC servo, under closed loop control, and we're now going to put it under open loop control and carry out an impulse response to work out the transfer function. So we're going to collect the data up now. So here's the impulse response, and you can see now a number of things going on here. First of all, here's the output here, more or less starts at 0 and goes up to this value here. So there's the shape of the impulse response, and this is the impulse here. So it goes along here, goes up to 1000, holds constant for 0.15 of a second, then drops back down again. So this is called the impulse response here, and this gives us this shape here. And then from this shape now, we'll be able to calculate the DC gain and the time constant, because it looks very much like a first order system response. It's not quite perfectly first order because it's got a little bit of a rounding shape there, but it's probably quite a good approximation to a first order system. And it's this data now that we're going to take to work out the transfer function for the system. I'm going to do that next. Right, so we're now going to go off to try and identify K and T, having done our impulse response on the system. So if we have a look now at the shape of the graph here, and we can see that this is going more or less halfway up between 200 and 300, so this must be about 250 there, so I'm going to make an educated guess, it's about 250. If I then take 63% of that value, draw a line along here, that's 0.63k, I can draw a line down there, that gives me this distance here as t. This is almost exactly the same as this distance here. So it's looking promising now for working out k and t. I can now get my k as 250. Now the impulse here is given by 1000 times 0.15, so that's 150, so the area is 150. So the impulse response is for an impulse of 1. So if it's an impulse of 150, we have to divide this by 150. So k comes out as 250 of 150, which is 1.66, and the time constant t as this from there to there, which is almost exactly the same as from there to there. Oh, I know that's 0.15 of a second. Now, in your case, it might not be that, but it's just lucky for me. So I've now got the k and the t, which means now I've now got my DC servo transfer function here, and I know that k is 1.66 and t is 0.15. So I've now got my transfer function, which I can then use for control system design. And that's what we're going to look at next, by looking at the design of using this transfer function to design a proportional control system and in it control the damping ratio. Right, so let's look at what we're going to do in terms of the feedback control. And we're going to split this up into two things. First one's called task 1, which is proportional control of a DC servo. And what we're going to do is here's the transfer function of the DC servo, here's a proportional controller, and we're going to simplify this down to a single block of the standard second order system form with the damping ratio and the natural frequency in, and then we'll know if the damping ratio is bigger than 1, it's heavily damped, equal to 1, critically damped, less than 1, lightly damped. So this is using our standard second order system thinking. Now, in addition, we're going to do task 2, which is to improve the performance by having a proportional plus derivative control. And we're going to have two versions of this. This is an S term here with the KDs. This is the extra part we've added in to add the derivative. But we can also add it in with this technique as well. This is position and this is speed. So if we use that signal there, the speed signal via the tacho through a tacho gain, through a gain kV, we can implement the two control systems. This one is susceptible to noise and this one is less susceptible to noise. We won't notice that much in simulation, but when we come to the real-time testing, we should find this one is more effective than this one. So we've got two proportional plus derivative control strategies. One is by using the proportional and derivative of the error, and one was using by proportional of the error and the derivative coming from the tacho and the velocity. So these are two different tactics. Now, in closed loop performance, if we've got proportional control, we can use this to set the damping ratio, which directly influences the overshoot. So with proportional control, we can really set our desired overshoot. If we use PD controller, we can set both the damping ratio and the natural frequency, which means we can control the overshoot and the rise time. So with PD control, we've got complete control. With proportional control, we've only got control over the overshoot and not over the rise time. So then we can get any type of response. We can get a slow response here, a nicely damped response, or a lightly damped response. And we've got control over this by choosing the controller gains. And if we know what the transfer function is, we should be able to choose the controller gains fairly accurately. Now, when it comes down to a second order system, we have a number of parameters here that we've used. This is the TP, this is the time to the peak overshoot. This is the peak overshoot here. and there are equations now which describe a classical second order system response. And just for completeness, here are the little equations which describe it. So here we've got our omega d equation, which we met before, the peak overshoot equation here, and the peak time one here, and there's a few extra ones in this, but these are your classic second order system response, and we're going to probably use this one to compute the peak overshoot as we go along, so I have to remember that one. And so we move on to task 2 now. This is proportional control of a DC servo. We've got to simplify this block diagram now down to a single block. So we can say that this signal here, which is the Y, is this times this times this. So it's going to be Kp times K over S Ts plus 1 times this signal here, which is the error V minus Y. So here's our closed loop system equation. And then we can move this term here up there. Then we can expand this term out and move over the Y terms as well. So it comes down to this. Now we can move these terms underneath here to give us this expression here. Now this one is looking similar to our second order system, but we've got a t in here. So we've got to get rid of that t. So to get rid of the t, we divide everything by t. So this gives kpk over t. T over t is 1, s over t, kpk over t. So this is our closed loop system equation now, starting off with this open loop. And for this one now, this is exactly the same as our second order system. So we know that term there is omega n squared, and this term here is 2 zeta omega n. So if we build on that now, here's our closed loop system equation, here's our standard second order system equation. So we know this term here, that's that term there, is equal to omega n squared. So there's our first equation. We know that 1 over t, because it's an s over t, 1 over t is 2 zeta omega n. So we can use these two equations now to try and simplify or get out an equation for Kp as a function of damping ratio. So if we take this equation, we got the zeta is going to be 1 over, just moving some of these terms underneath here, zeta is 1 over 2 omega nt, or omega n is 1 over 2 zeta t. So if we square this expression here, we'll get omega n squared is 1 over 4 zeta squared t squared, but omega n squared is the same as this first term here. So that's equal to kp, k over t. So this is equal to this. We can cancel one of the t's out and just move that k term underneath with these terms here. And we get that kp is 1 over 4 zeta squared tk. So this is a lovely little expression now, which allows us to choose a damping ratio. If we know what t and k are, it'll give us a kp. So this allows us now to do a little bit of simple design. So we've got this expression, kp is 1 over 4 zeta squared tk. Now from our previous testing now on the DC servo, I'd worked out my t was 0.15 and my k was 1.66. Now these will be different for you because you'll have worked them out for your particular servo, and every servo's slightly different, but you'll have numbers similar to these. So you've got your t, you've got your k. You can stick these numbers now into this expression here, and you know for different damping ratios. So you can choose a damping ratio of 0.5, put that in there, put t in there, put k in there, get a value for kp, mine comes out as 4. Then we can increase the damping ratio to 0.6, the gain comes down to 2.78, increase the damping ratio to 0.7, gain comes down to 2.04, increase the damping ratio to 0.8, 1.56, damping ratio of 1, by chance it comes out as 1. Now I know for a given damping ratio that if I put that number into here, this number comes out as 16.3. So if I've got a damping ratio of 5 and it's 16.3% overshoot, damping ratio of 0.6, 9.48, 0.7, 4.6, 0.8, 1.5, and 1, no overshoot at all. So let's have this little table now, which tells me if I choose a Kp of 4, the damping ratio in the system will be 0.5, and we'll have approximately a 16% overshoot. If I chose my damping ratio as 0.7, I'd have a Kp of 2.04, and that would give me less overshoot at 4.6. So this table now, I can look at the performance of the system by running simulations of the closed loop system with these different gains in. So here's my table. I'm now going to have a Simulink simulation set up like this. I'm going to put the KP values in here and look at the system performance. The first one to look at is proportional control with damping ratio as 0.5. Now going back, it was 0.5, my KP was 4. So if I stick 4 in here now, simulate this closed loop system, I'm going to put K as 1.66, T as 0.15, simulate the system in Simulink, and I'll get the transient response here, and this should have an overshoot, peak overshoot of 16.3%. So let's see if I can do this now. Seem to have lost control over my screen. So that's right. So here we go now with that proportional control damping ratio of 0.5. We've got from the previous calculations that for damping ratio of 0.5, so a gain P of 4, which should give me a 16.3% overshoot. So let's see how we're going to do this now. So we need to simulate this in Simulink now with K as 1.66, T as 0.15, and KP as 4. So I go to my Simulink now, and here's my Simulink block diagram. So got 1.66, 0.15. Here's my simulation. The gain's wrong now, so I click on this box here and set the gain as 4. Type OK, and then run the simulation. I will then get the transient response, which is like this. And this has got the 16.4% overshoot there. I'm going to copy this, go into File, copy to Clipboard, and I can use Paste to put that into my report. If I go back now to Simulink, so I'll go for the next one, which is damping ratio of 0.6. Now for damping ratio of 0.6, I need a slightly lower gain, 2.78. So as my gain reduces, my damping ratio goes up. They're inversely proportional to one another, and this should give me about an 10% overshoot more or less. So I need to change the gain in here now to 2.78. So 2.78, here we go. So go into Simulink now and change the gain to 2.78, and then run this one. Look at this, and now we can see that's 9.48% overshoot there. You can see it's about in the middle, almost about 10%. So that one looks pretty perfect. Now we can go to the next one, which is a damping ratio of 0.7. So with 0.7 now, the gain reduces, remember from our table, 0.7, it's 2.04 now. So at 0.7, the gain is 2.04. So we'll go back to my Simulink and put the gain as 2.04. Click OK, and then run the simulation. Notice the simulation's time is set at 2 seconds. I found 2 seconds quite good. And notice though, as we run the simulation, the time of peak overshoot is moving down this way. So we reduce the gain, the system doesn't have as much overshoot, but it slows up as well. So originally we were over here somewhere, it's coming up a bit faster. Now it's a bit slower. So we're controlling the damping ratio in this, but we're not controlling the settling time. As we add more damping in, it slows up the response. So we're not, proportional control isn't the ideal ticket here really. If we go for 0.8, the gain is 1.56. So we go back to our Simulink. This is now going to be 1.56. So we put that in there, run the simulation again, and here we go. This time you can see it's got only this time 1.5, or very slow. It's about 5% overshoot this time, but notice it's slowed up again. So that was our simulation with damping ratio of 0.8. 0.8 actually had 1.5% overshoot. If we do the last one, which is damping ratio as 1, we need a gain of 1. So this was coming from our table, remember, which we'd worked out. So damping ratio of 1 by chance, my KP was 1. It was only by total chance. But that's how it is sometimes. Sometimes you win, sometimes you lose. So we need a gain of 1 in here now. So we go back to simulation and put a gain of 1 in here now. We're going to reduce the overshoot to 0, which could be handy, but you can see we paid a price. It's quite a slow response now, so no overshoot. but quite a slow response. It's taken almost a full 2 seconds to get there, whereas originally it was after about 0.8 of a second. So it's significantly slower now, isn't it, with a damping ratio set at 1. You've lost quite a bit of performance, the price of overshoot. If you go back to the 0.8, which is a gain of 1.56, even 1.56 doesn't like a comma in MATLAB, it'll just crash. We run this as a damping ratio of 0.8. You can see it's quite a bit faster at 0.8, but the peak time is about 1.2 seconds. Whereas if we go back to that one that was 4, that's a damping ratio of 0.5. It's got quite a bit of overshoot, this one. Notice now the peak time is only about half a second, so it's much faster, isn't it? Much faster response, but you're paying the price for this big overshoot. So if I was going for this one, I think I would choose here 2.5. It's going to give me something quite nice. It's going to give me that, so that's got about a 8% overshoot and the rise time of about 0.75 of a second. So that'd be my compromise, but everyone's got their own choice. But that'd be one of my better results. I was doing this, and that's with a gain of 2.5. So if we just go back to the quick summary then of our proportional control, we can work out K and T. We can then choose our KP based on the simple expression here. So if we know what the damping ratio is, we know what K and T is, we can dial in this equation to give us our KPs. That'll give us then a guaranteed damping ratio in the closed-loop system, which will give us a certain overshoot then associated with it, but it won't control the rise time. But we could control the overshoot through proportional control, and by choosing different gains we get different damping ratios, and we can choose essentially the overshoot. That's the thing we can do with proportional control. We can choose our overshoot. We can't choose our rise time. So in order to go to the next stage, we need to look at proportional plus derivative control. So in this one, we can control both things, both rise time and the overshoot. Right, to improve the performance, we can add derivative control. Now, this amounts to what's called a PD controller. So we have proportional control, like we had before, proportional, and then we have derivative, and we have the derivative in the Simulink block diagram by using the du by dt. So this corresponds to an S term, if you like. So that's like an S. Simulink doesn't have a specific S term, it just uses du by dt to represent S. So this is a PD controller, and this is an alternative that we could use as well. If this is the output here, which is say position, then this would be velocity, the signal here. So if I measured this signal, it'd be velocity. So velocity is the same as the derivative of the position. So rather than using the derivative signal here, we could measure the velocity here and feed that one back. Now, in our particular design, we use something called a tachometer, and that has a slightly different gain, which we have to work out beforehand. And then we have to ensure then that this gain of the tachometer multiplied by this gain here, which I'm calling kV for velocity feedback, is the same as kd. So as long as kd is equal to that times that, these two block diagrams will perform in a very similar manner. Now, you might want to say, well, why bother with this extra one? Well, this first one turns out to be more susceptible to noise. So in a simulation, if we don't have any noise in the simulation, they'll both look the same. But when we come to the real application, we might find that the second one is better than the first one. So let's look now at task 3. So this is proportional derivative control, and we're designing control of the form Kp plus Kds. So S is the d by dt term, it's giving us the derivative. And we've also got in this thing something called the tacho amp gain, which is the gain of the velocity feedback here, and for the example I'm doing, my gain is 0.333, but for your rig, each rig has a slightly different gain, which will tell you on the day. So technically, you can use a PD controller to control a DC servo. However, sometimes there's noise on the position sensor, which makes the derivative of noise ineffective. So to use this, to get rid of this problem, we can add in an additional sensor to get a derivative signal. And in this particular case, it's called a tachometer, and it's basically a speed measuring device. So it costs you a bit more because you've got to have two sensors now, but you might get a better performance from your servo. So let's look at the proportional plus derivative design. So this is our block diagram. We could take this block diagram now and simplify it down to a single block. So this is what it comes out as when it's simplified down to a single block. And this is the same now as a classic second order system, s squared plus 2 zeta omega n s plus omega n squared. So this part here is the same as this. Notice it's been made to have just an s squared term there to be the same as that. Now, when we've done that, we can say that this term here is the same as this one here, and this term here is the same as this one here. So we get two little equations. Omega n squared is k kpt, and 2 zeta omega n is 1 plus k kd over t. And we can see by just playing about with this equation here, rearranging, we can get zeta is 1 over 2 1 plus k dt. So this gives us by rearranging these equations, we can get an expression for the damping ratio. Now, what we're actually going to do though is this. Here's our closed loop system. Here's our second order system. We know that term is the same as that one. So we can get some little equation now that this is equal to this. So that's equal to that. And we can rearrange this and we get the Kp is simply omega n, the little t is underneath there, so it becomes on the top, and the k goes underneath. So Kp is t omega n squared over k. So if we were to choose now zeta and omega n in our design, the fact we've chosen an omega n, we can stick the omega n in there, we get a Kp, so we know what the gain was. Looking at this part here now, this part here is equal to this part here. So that gives us that 1 plus k times kd divided by t equal to 2 zeta omega n. We can rearrange this now for kd. So move the t up there, move the 1 over, and then divide by k. So kd is 2 zeta omega n t minus 1 over k. So again, if I've chosen the damping ratio, I can dial that into this and get kd. So for this design, I can choose a damping ratio natural frequency for this system, which completely defines the performance of the system. And I can get two simple expressions now for working out what the gain should be, just by sticking in my chosen damping ratio and my chosen natural frequency. This gives me a nice design method now for designing proportional plus derivative controllers. And this is a table now where I'm going to work some stuff out. So here's my different damping ratios, and in this particular case I'm going to stick to the same omega n. So omega n at about 7 radians per second is about 7 radians per second is about 1.5 revs per second. This is about as fast as that system, the rig that we've got, will go. So I've chosen this as 7, but you could have chosen it as something else, but I've chosen it as 7 because it suits the rig. So if we have got omega n zeta as 0.5, omega n as 7, I can stick now. I've got my equation for Kp and Kd. I get the Kp is 4.42 and the Kd is 0.03, and so that's going to give me, with 0.5, I get this 16% overshoot. If I go to 0.6, because this equation is always the same, so the gain Kp will always be the same, but this value for damping ratio Kd now will increase as we increase the damping ratio. This number will increase as well. So put 0.6 into this equation, get 0.16, 0.7 into this equation, get 0.28, 0.8 into this equation, and I get 0.41, put 1 into this equation, and I get 0.66. So this is my table of gains now for Kp and Kd to achieve different damping ratios, but the same natural frequency in the performance of this system here. So here's now, we also know that we need a kV value as well for our practical work and also for running this simulation. So because this gain here is 0.33, this times this has to equal to this. So therefore this number here, in my particular case, will be 3 times this. So if I take these numbers here, multiply them by 3, that gives me these numbers here for kV. So I've now got a complete set of numbers. Got all my KPs, all my KDs, and all my KVs to put into this design. Put the KP in there, put the KD in there, and the KV in there. And then I can start now looking at the simulations. So I want KP equal to 4.42, KD equals 0.03, and KV equals to 0.09. So I can now move on now to my Simulink simulation. So here's my Simulink simulation now. So I go for KP, click on that one. That's going to be 4.42. My KD is going to be 0.03. And I'm going to have to change KP here as well. So I've got, this is going to be 4.42. Fortunately, in all my simulations, KP is always 4.42, so that means I'm going to change too many things. And this one is going to be 0.09. Something like that. Put a comma in, so it's going to be 0.09. Can also make a little mistake. And this is at 0.333 here. So this is particular for my rig. One of you probably will have the rig that I've got, in which case it will be 0.33, but the others might have a slightly different number there, so you'll have to ask on the day what number to put in there. So here's our simulation now. This has got 2 outputs. It's displayed here, the top one, the bottom one's displayed here, but they're both displayed on this scope here simultaneously. So these 2 designs should be more or less the same because they should represent the same type of feedback. So if we run the simulation now, and wait for it to run. It's running a bit slow on my computer today. And then click on this box here. We get the transient responses. Here we go. And if you notice now, it just gets one graph indicating that both are plotted simultaneously on top of each other. So it's just showing that they're identical. Just to prove that, if we change this number here to, let's say, 0.5, and that just for a moment, and then run it again, we now can see this because that changed. There's some difference. So there's 2 graphs there, but they're both on top of each other. So if you make a slight change here, they will be a little bit different, but they weren't that much different, were they, considering we changed this by about 10%. So there's a 10% change in the system, and the performance didn't really degrade that much, did it? So that's another thing you can look at in control systems, how much things degrade if you change the numbers. It's called robustness. But I'll put this back to 0.66, and off we go with the same thing. So we can now, looking at this response again, if we just run it again. So here's the response, and this has got now that 16% overshoot, and TP is about probably half a second, isn't it? Half a second. If we go back now, so that's our transient response here, and this is the same graph really. So if we move on now, this was a damping ratio of 0.5 and make it -7. If we now go for damping ratio of 0.6, the difference now is that KV is the same, but KD is only 0.16, and the KB is 3 times that, which is 0.48, 3/16, 48. So this is going to give us like a 10% overshoot here. And notice again, the TP is about 0.6 of a second. It's a bit less than 0.6, about 0.55. So go back now into our simulation, and we change now this gain here. So it's going to become now 0.16, and this one is going to become 0.48. No, it's 3 times bigger because it's got a gain of a third here. And if we run this now and look at both, again, you can see it's a little bit different there, but it's so small you can hardly see. It's the thickness of a line, isn't it? Almost identical response, and this time we've got the 9.4% overshoot because it's a damping ratio of 0.6. Move on to damping ratio of 0.7 now. So this time KD goes up to 0.28, and therefore KV goes up to 0.84. So these are the new gains. Remember, KP is constant for this because of our chosen omega n is 7. That sets the KP. It's quite handy. So go back to this one now, and we change this now to 0.28. And this one now to 0.84. 0.84. And run this one. And this time, here's response again. You can see this time we're going to go about 5% overshoot. So we get a reduced overshoot on this one. That should be, it's 4.6%. I should have lost my piece of paper there with all my things on. So that's 4.6%, almost 5%. So if we go back to this one now, see that's about 5% there, 4.6%. If we go to 0.8, then the KD value has now gone up to 0.41 and the other one to 1.23. So I'm looking now at hardly any overshoot at all. It's about 1.5% overshoot. This one's quite a nice response. I like the damping ratio of 0.8. Seems no overshoot at all, really, but quite fast. Notice this is coming up in about 0.8 of a second, isn't it? We'll go back to that in a minute. Let's just go to our Simulink and change the gain now from 0.28 to 0.41. So as we add 0.41, as we make the KD bigger, we get more damping, and this one becomes 1.23. We're running both simultaneously, which is so to show they're both the same. So here this one done, and again here's a response. So it's quite fast, hardly any overshoots at all, and the time for peak is probably about 0.7 of a second, isn't it? 0.7 of a second. So there's a response with 0.7 of a second. We just go back quickly to the proportional control at 0.8. This is the just proportional control. Notice the peak overshoot here is about 1.2 seconds. So with the derivative, it's really sped up, and we've got it to come up at 0.8 of a second. So it's quite a bit faster. It's about almost 50% faster, isn't it, with the PD? So the PD is doing better than the proportional. So that's why you get a faster response with your PD than you do with your proportional. So that's why it's attractive to put that extra signal in here, because you can get more out of your servo. Let's go back to here now. So it's 0.8. The last one is 1. Damping ratio is 1, and this time the gain is quite big now, 0.66 or 1.98. It's quite close to 2, that, isn't it? So if we do the last one now and go in here, this is going to be 0.66, and this is going to be 1.98. Didn't like that. 1.98, and you've got to click on OK to make sure it goes in. So if we run this one now, this is damping ratio of 1, and if you look at this, so here's the response. So it's about, again, it's coming up in about 0.8 of a second. So it is much better than the proportional control. The proportional control took almost 2 seconds, didn't it, to sort of came up like that. So you can see now this big advantage now in having proportional plus derivative control, and that's why most servos have proportional plus derivative. So in summary now, we can have, these are the two sort of block diagrams we could have for PD control. We can set now a damping ratio, set an omega n, and then we've got an exclusive on there, a simple equation, which is like a nice one-to-one relationship between omega n and Kp, and a nice one-to-one relationship between damping ratio and Kd. So some little formulas here, we can stick omega n into there, get Kp, stick damping ratio into there, get Kd. That sets then what the damping ratio and natural frequency is for our second order system. And if we're using derivative control, we need to know what the gain is there, and then this is like has to be taken into account to get the kVs. And then this, because it's the damping ratio and this overshoot are uniquely fixed through another equation. As soon as you achieve these damping ratios, you're going to get these sort of overshoots. But in this particular case, we're also able to control the rise time as well. So if we change this number here, we could change the rise time. If we change this number here, we could change the damping ratio. So we've got complete control over the whole thing, which is very pleasant, isn't it? So in our next stage, we're going to look at the practical servo trials, and that's what we're going to talk about next. Okay, so we're back to our task form, practical servo trials. This is going to be where we're going to use the DC servo now to actually get some results. So we're going to use the controllers designed in tasks 2 and 3 to do this. And we're then going to enter those controller gains onto the servo and get some real responses. Now, so we're going to look at task 2, the proportional controllers, and then task 3, the derivative controllers, where it's the PD controller, and then the PD controller where we're using the tachometer to get our derivative signal. Now, this is going to give us quite a few results. So the first set of results we're going to get are just by putting the system under proportional control and trying these different gains here. So you've got a little table now which you've developed for your Kp, which you've simply got by putting these equations into here. And these are the gains we're going to try, and we're going to get 5 different results out. So you need to make a note now of which is which. You can tell because in the bottom left hand corner of the simulation or the real-time results, it'll tell you what Kp is. So if you get confused, you can look at that number. Best plan is to take a photograph of the screen as you're going along, and then you'll get some nice results. So having done that one, we're then going to look at this one here. This is the PD design, and this one now might be susceptible to noise, so we can see what happens. But for this one, you've got your proportional gains and you've got your derivative gains. So again, you're going to get 5 results here, 1, 2, 5 different results for different damping ratios. And that's going to be another set of 5 results, and then you're going to get the final set of 5 results by looking at this arrangement here. So this time we don't use Kd, we set Kd as 0 and we put in the Kv value. So in one design you put in Kd, the first design put in Kp and Kd, Kv as 0. In the second design you put the Kp in, the Kd as 0, and put these values in for Kv. And then you'll get another set of 5 results. So you then have 15 results then to do a comparison with. So we're now going to go off and do the results. And having done the results, then we're going to look at comparing the 3 sets of results to see what we think of the performance of the DC servo for real against, and then compare it with our simulation. Okay, so here's our first one, proportional control. Kp is 4, and this gives us a damping ratio of 0.5. So we put in now 4, 0 for Ki, 0 for Kd, and 0 Kp, and we now get the closed loop set response, and there it is. So this is now showing us this is Kp as 4. So the next one we're going to do is proportional control, this time with a KP of 2.78, dampen this of 0.6. This is now damping 0.6, and we can see slightly different response here. So there's the one with damping of 0.6. The next one we're going to do is proportional control, this time with damping of 0.7, KP this time is 2.04. Okay, so there's the damping of 0.7, KP at 2.04. The next one we're going to do is proportional control. This time KP is 1.56 and the damping ratio is 0.8. So we're going for a damping ratio now of 1.56. Damp ratio 0.8, so it's going to be KP is 1.58. So it's going to be 1.58, 0, 0, 0. Okay, so this is a damping of 0.8, and that's the response with damping of 0.8. The last one to do in this particular set is proportional control with KP as 1, which by chance gives us a damping ratio of 1 as well. So this is the last one to do, damping ratio of 1. And there we have now the response with the damping ratio of 1. Okay, so in this test we're going to do now proportional plus derivative control, and in this particular case KP 4.42, KD 0.03, damping 0.5 and omega n 7 radians per second. Okay, it's going to be 4.42, 0, 0.03, and nothing for KB. So this is the response here, and we can notice now, just notice a little bit of noise creeping in now on this signal here. So it's just got a bit more noisy as we put in the derivative, and as we notice, as we put more derivative in, this signal here will get, this is the voltage applied to the motor, this will get more noisy as we go along. So the next one we're going to do is the proportional derivative control. This time KP sticks at 4.42, but this time the KD goes up to 0.16, so we're increasing the damping ratio from 0.5 to 0.6, and we're keeping omega n as the same. So we can do that by K 4.42, 0, 0.16, 0. So notice now there's even more noise now on here, and this is the response we've got. So the next one we're going to do, let's look at that again. Okay, so the next one we're going to do now is this one. It's the proportional plus derivative control. This time Kp is the same. Damping going up now to 0.7. So Kd's gone up to 0.28. Omega n is still 7 radians per second. This is a damping now of 0.7. Notice now what's happening is as we're getting more and more noise down here. This response isn't too bad, but we get a lot more noise on the system. So that one's damping of 0.7. So next one is to put more damping in. So again, this time we're going up to proportional derivative control. Kp 4.42, Kd is somewhat to 0.41, damping pressure 0.1, omega n still 7. So we have the damping of 0.8 now. Notice now this signal here has got very noisy indeed, as it's amplifying the noise. And a little bit of loss in accuracy in the system as well. But it is controlling it with a there's no overshoot, is there? So the last one we're going to do is proportional plus derivative control. Kp as 4.42, Kd as 0.66, this time to gives a damping ratio of 1, and omega n is still fixed at 7 radians per second, so this is damping ratio 1 now, Kd is 0.66. Have a look at this. So it's well damped, but very, very noisy down here now, and there's a bit of like error coming into it because the noise is inducing some error into the confusing the control system. So it is working, and we have got like a very damped system here, but this signal is very noisy. So that's our proportional plus derivative for a range of damping ratios. Right, so here's our sets of results now for proportional derivative control using the velocity feedback. So Kp 4.22, Kv 0.09, damping ratio 0.5, and natural frequency still 7 radians per second. It's 4.4200 and 0.09. So here we have now using the tacho. There's the transient response there. So one of the things to notice about this one now is how little noise there is on this signal here. It's a very clean signal, that one, because the tacho is providing a much cleaner signal than differentiating the potentiometer. So there's our first result for damping ratio of 0.5. Okay, so here's our next one. This is proportional plus derivative control. Kp 4.42, Kv 0.48, damping 0.6, omega n 7 radians per second. That's the velocity feed, it's the tacho feedback. there's our transient response this time. We can see again a little bit of noise in here, but not much noise, and that transient response typical of what we might be expecting to see. So here's the next one now. This is proportional plus derivative control. KP 4.42, KV 0.84 this time for damping of 0.7, omega n still 7 radians per second. So here the damping now at 0.7. And again, quite a small overshoot there, which is what we expect with damping of 0.7. So that's the one with a tacho. Notice again, nice smooth signal here. Right, so here's the next one. This is with the proportional plus derivative control. KP 4.42, KV 1.23, damping ratio of this one 0.8, omega n 3 radians per second. And there we have now this is a damping ratio of 0.8. You can see this is a minimal little bit of overshoot here. A little bit of a steady state error creeping into this one. This is due to an offset in the potentiometer that's, well, in the set signals conditionings unit that's measuring the tachometer. So unfortunately my experiment isn't perfect here. But the green line and the red line should be on top of each other if it was working correctly. Okay, so here's the last one now. This is with proportional derivative control. KP 4.42, KV 1.98 this time, damping ratio 0.1, omega n still 7 radians per second. So here we have the case with the damping ratios 1. Unfortunately, in this case, the signal conditioning unit isn't quite right. You can see it's very heavily damped, and ideally those two lines should be on top of each other, but for my particular experiment, unfortunately, they're not. Okay, so now we're going to look at review the results from the simulations and from the practical results as well that we just obtained. And looking at three things really, but some of the things we're looking at associated with this table here, but also with the table for proportional control. So this is now a comparison of our results. This is a damping ratio of 0.5 and the different results you obtain from there. So this is proportional control, damping ratio 0.5. This is proportional plus derivative, damping ratio 0.5. This is the practical result of proportional. This is the practical result of the proportional plus derivative, and this is the practical result of the proportional plus tacho. So we can see from these that broadly the amount of overshoot, they all look very similar, don't they? Because they've all got this damping ratio of 0.5. The next one, we've got a damping ratio of 0.6. So again, the overshoot there, they're going to be the same. And again, these overshoots here are looking quite similar. This one's looking a little bit low, isn't it? And this one's got noise in. The noise can affect the performance of the system. So actually, I've added a bit of damping in by mistake. So that's the damping of 0.6 for all different results. This is now the 0.7. Notice now we can notice a little bit that the rise time here is definitely faster than the rise time of proportional. And we've gone for an omega n of 7 in the proportional with derivatives designs. So we've got a benefit now of having a slightly faster response than the proportional control. But again, looking at these practical results, this one looks more or less the same as this. This one looks the same as this. This one's a little bit underdamped or overdamped. But as a family of results, you can see they all fit in There's just a little bit of overshoot, a little bit of undershoot type transient response. That's our damping ratio 0.7. Then when we got to 0.8, again you can see more markedly this time that the rise time of the proportional control is slower than the rise time of the PD controller. So there's a good benefit between those two, and we can see here that all of these are not really giving us much overshoot, or they aren't giving any overshoot. Hardly noticeable. It's in this of 1%, so you can't see it. Slight error in the potentiometer on the offset on the tacho here. It's a bit annoying. That green line and the red line should have been on top of each other. And finally, we've got damping ratio of 1. So this is, again, you can see the rise time of the PD is faster than the rise time of the proportional. So there's some advantage in having your PD, and all of these results, they all look in the same family of results, with slower but with no overshoot. Those looks, the rise time there looks like the rise time here. The rise time there looks like the rise time there. So they look a consistent set of results. So let's have a look at our discussion and conclusion for what main points we want to look at. We looked at the identification of the transfer function using an impulse response. You could discuss that. You then use the transfer function to work out a set of proportional controller gains, such we have a whole range of damping ratios in here, so you can discuss that. You can then look at how you looked at you've used Simulink as well to compare. You've designed the gains and you've used Simulink to get some transient responses. So you've got the proportional gains and the transient responses. You then looked at proportional but derivative control systems, doing the same thing as you did here. And then you've compared the simulation results with the practical results. You can have a little discussion about the effect of noise on the derivative controller. And I think the main thing is how derivative control can add damping to a servo system. If you've got proportional plus derivative control, you can do it without paying too much of a price in terms of loss of rise time. So they're your main points for putting in your discussion, and maybe that last few points are the things that might go in your conclusion.